We are proud to represent Holland and Smith Engineers located in Marietta, Georgia. Thank you for giving us this opportunity to present our work today. This presentation is in regards to the Kimberly-Clark Amphitheater in Roswell. In early 2020, we were awarded the task of preparing plans for the amphitheater by the city of Roswell. The scope of the plans presented here includes site planning and layout, hydrology, geotechnical reporting, and structural plans for the amphitheater. First, a bit about our process. Working for and within the city of Roswell, we first thoroughly research relevant site development and structural codes, specifically the Roswell Unified Development Code and standard construction specifications. These can be found online. Here is the Roswell zoning map, and the site is highlighted in blue there in the center of the map. Notice it is in the Office Park Employment District of Roswell. The site location is 7.64 acres of undisturbed land nearby the Highway 400 and the Vulcan Bridge Road intersection. When all is said and done, there will be 2.47 acres of paved surfaces, including parking, driveways, and all of the sidewalks. In regards to site planning, we worked closely with our client to make sure the design we came up with exceeds all of their expectations. A few of the City of Roswell's criteria for site planning include a parking capacity for 150 cars, access driveway and capacity behind the stage for 5 vendors, such as food trucks, sidewalk access across the property, tiered amphitheater seating for at least 450 people. The first step in the process once we had plans for the topography of the site was to decide on the best location for the amphitheater and parking lot. By looking at the natural slope of the land, we decided to place the amphitheater stage at a low spot on the north side of the site. The grade levels out some on the southwest portion of the site, so we decided to put the parking lot there. The existing contour lines are shown in light gray and the post-development lines are the darker black. To the extent possible, we tried to limit our disturbance of the existing topography. This helps keep project costs low. By using the AutoCAD Civil 3D Volumes tool, we analyzed the total cut and fill of the new grading plan. The net volume is 2,305 cubic yards of fill. As mentioned before, the entrance to the site is accessible from Market Boulevard. This is a dead-end public street. Both Market Boulevard and the driveway entering the parking lot will only serve as access to the amphitheater. Therefore, there will not be any through traffic. The proposed driveway is 28 feet wide, from back of curb to back of curb. It provides two-way access to the parking lot. The required length of the ingress-egress before entering the parking lot depends on the maximum peak hour volume. Since the parking lot has a capacity of 164 cars, the maximum volume entering or exiting the site is expected to be less than 200. The 280-foot driveway is plenty long. The curbs and gutters were designed from the City of Roswell standard design specifications, and they match the curbs and gutters on Market Boulevard. The parking lot was designed after carefully researching the code requirements for Roswell. Each of the standard spaces are 9 feet wide. For every 200 cars, 6 accessible parking spaces are required, and 1 van accessible space is required. Also, at least 5 motorcycle spaces are required for lots with over 150 passenger car spaces. Everything from the trees on the median to the spacing between rows was designed according to Roswell codes. The desired capacity for amphitheater seating is 450 people. This is calculated by assuming that one person will take up 2 feet of bench space. With 3 sections and 9 rows, our design will hold 456 people. In addition, the grass field behind the seating can hold several more hundred people. The assumption is made that spectators need to be within 90 feet of the stage to see and hear well. The bench seating is tiered at a slope of 25% or 1 foot horizontal for every 4 feet vertical. In between each section is a 6 foot wide path with steps leading down to the stage.
The Kimberly-Clark Amphitheater was intended to handle any kind of event from a small-scale preschool ballet recital to a production-heavy concert. To achieve this, we designed a layout that gave us an entirely open floor plan with a big 34-foot by 22-foot stage and a 34-foot by 12-foot backstage. There were a few special considerations for the project. For example, each beam in the stage area was designed to withstand the typical gravity and lateral demands, as well as a 300-pound per linear foot line load to accommodate for props, lighting, pyrotechnics, etc. Concerns about the roof deck vibrating and creating noise pollution during concerts were also dealt with by upgrading the typical deck to a Volcraft 2.0 DA acoustical dovetail roof deck. This product reduces vibration while far surpassing the mechanical properties required by the design. 4 of the 6 spread footings were upsized from a 3x3 foot footing to a 4x4 foot footing for ease of construction while also reducing the possibility or the severity of any settlement. Now each of the footings' exterior finish face match up with the slab's finish face. I used Revit to do my modeling because it delivers a higher quality product in my opinion than AutoCAD. It's nice to be able to view the project in 3D because 3D is just better than 2D. That's why it costs more when you go to the movies. Perhaps a better justification would be how when you're working on large multi-story projects, it's highly beneficial to look at the structure in 3D and then tell if you have a consistent load path from the top to the bottom of your design. In this project, it wasn't so vital. Here, the overall intelligence was more so what drove me to pick Revit. Um, Coordinating details from what's called out on the plan is much easier than in AutoCAD. All it takes is reassigning your property to tell your detail that you want to change your joist to a beam, whereas in AutoCAD you would have to redraw that entire object. To start the design, I gathered the information I would end up needing in the analysis software from ASCE 716. Things such as the loads, the risk and seismic design categories, and also the site class. Those were just some examples of the inputs needed in InterCalc to generate the lateral design parameters and factors, the big ones being the spectral acceleration and the response modification factor. With this report, I had the values I needed for RAM to run the gravity and lateral analysis. Once in RAM, you have to work your way through the 5 modules: the modeler, the beam, column, frame, foundation module. The first 3 are fairly straightforward. You create a layout, apply the loads, and it gives you the beam, joist, and column design for gravity. The frame module requires the previously discussed values to design and test the structure under that lateral loading. This module also checks for code compliance and creates reports on the structure's performance. One aspect of performance analyzed is the drift of the structure. Here you can see an example of a drift report which shows how much the structure moves under different loading conditions. The maximum drift was limited to around 1 inch for serviceability purposes. Though it went over in 2 of the combinations, they were still within acceptable margins. At this point, RAM has supplied the member designs, but before finalizing the design, I double-checked the beam sizes in InterCalc. If the beam sizes and reactions are the same, that's a pretty strong indicator that the subsequent columns and footings will also check out. Now, all that was left to do was coordinate my Revit model with the designs from RAM.
Hi, my name is Austin Smith. I'm going to be going through the Kimberly-Clark Amphitheater site hydrology. I was responsible for its design and layout, and we're going to run through everything and then wrap it up and then hand it off to Kevin for the geotechnical portion. So real quick, I wanted to keep it light in terms of stuff on the screen. I'd rather have my presentation and talking to a little bit more. So pre-post conditions, we can run through real quick into the through these items. So we're going to look at the pre-post conditions, the yard piping plan, and then ultimately the storm water management pond. Okay, so pre and post conditions, we evaluated the site using the Georgia Stormwater Manual in its sections on water quality for detention, as well as did some things with City of Roswell's ordinances, as well as using TR55, NOAA, and SCS as the basis of the data that we used in those calculations for using with the ordinances in the Georgia Stormwater Manual. You can see here our site drainage basin. Our actual disturbed area was only 6.34 acres with a overall undisturbed combined CN of 78. You can see the drainage, the time of concentration is actually supposed to be a 1 right there. 15.84 minutes. You can see 100 feet of shallow flow, 536 feet of concentrated flow, and then 153 feet of channel flow. And then switching over to our post developed site layout, you can see the drainage area A, drainage area B. You can see the differentiating CN numbers there, which you can see the calculated weighted CN down there. You will see, then you'll see the difference: 100 foot of sheet flow here, 684 feet of channel flow as for our time of concentration calculation in our impervious areas. Okay, which comes out into a graded spillway, and I'll get to that. So jumping into our pond design, the natural spillway backs up here, which will flatten the water out, slow it down. You can see what you're looking at is was not the first design, making it as blocky and as constructible as you can, and then looking at the space you have. We wanted to consider more vendor parking, more vendor area, so reduction of the pond while still fitting it in, refining it over again, and coming up with this. You can see it's our technically titled our SD3-A. You can see the use of our micro pools, A, B, and C. You can see the safety bench between them. You can see we use riprap type 3 aprons for all flows into the pond. You can see here our hydrograph volume that needed to be captured. Okay, and then we're going to go to a cross-sectional cut. In our cross-sectional cut of the pond, you'll see the 1 year, which is mainly captured by the micro pools. You see our 1 year water elevation, the water quality elevation, which the calculations for that are provided in the notebook. You can then see our 25-year, our 100-year water levels, which we took care of release by using a 8-inch orifice, a pedestal weir, which is 1 foot by 6.5 feet, a 8-inch orifice with a PVC line, and a 3-inch orifice to capture our water quality. You got a 24-inch pipe leaving out. You got the bottom there. You got the inflow. We have a plan view, 6-inch walled precast OCS. Nothing crazy there. Something a little different we did, looking through some of the Army Corps of engineering resources. We wanted, since the OCS sits not as deep traditionally as you might find an OCS sitting in a water detention pond, we wanted to utilize something to not have to go with a concrete cradle or a unique geotechnical solution under and around the pipe. So we ended up going with a anti-seep collar, which there is an additional anti-seep collar before the head wall outfall of this pond. And with that, that is a three minute and some change review of the site hydrology. I urge the review and to look back through the notebook for the nitty-gritty details. Thank you, and I'm going to pass it off.
We are using a hollow stem auger. that is also equipped with a split spoon, which means while it's drilling and counting the blows, that it also collects the soil material that it is drilling through, and that material is then collected, usually placed in a trash bag or a Ziploc bag, and shipped over to one of our labs where we analyze and determine the classification of the soil. For this project, we bored in 6 different locations, 3 being in the building pad and 3 also being in the proposed parking lot. The building pad boring terminated at 15 feet, while the parking lot boring was done at approximately 10. From the augers data, we are able to form a boring log. This boring log is at P1, which means it's in the parking lot, and you see what sample was collected on the left side of the log. You see about 3 feet of topsoil, and then you have a 3 feet we determined loose sand, and then you have clay material for the remainder 4. And the end values are determined by the last 2 digits of the blow count. As for the topsoil, you have 2 and 2, which gives it a end value of 4. And for the sand, you have 6 and 5, which gives it for 11, and so on and so forth. Once everything was aligned, we started with construction. We started excavating. Since this place was a heavy wooded area, we made sure that all organics were removed, all the trees, the roots. So that's why in the previous slide you saw the boring log, a topsoil of about 3 feet. We got rid of all that topsoil. We dug down until we got a nice, firm, solid base. Once we felt like we got there, we proof rolled the area to determine that there was no rutting, no pumping, and that the area was stable enough to start backfilling. Once the excavation started, we collected all the different types of soil samples on site and sent them to the lab to create a Proctor curve and to see if all that material is deemed suitable for backfill. The Proctor curve showed us the water content and the dry unit weight of each soil material and the perfect conditions for each material. So when used for backfill, make sure that soil is in that or around that condition. Also, if the GAB used on site was also in our lab, and a Proctor was also formed from that as well. Once a Proctor curve is determined for all soil that are being used as backfill, and once backfill starts, we tested each lift. Approximately each lift is maybe 6 to 8 inches. There are 2 types of testing methods that we use, and that is the driving ring and the nuke gauge. The driving ring takes a lot more time than a nuke gauge. Nuke gauge, you can get results as quick as a minute. As far as a driving ring, where you have to drive the ring into the ground, dig it up, weigh it, cook it to get all the moisture out, and weigh the soil after it's cooked to find out the moisture content, compared to a nuke gauge where you just drive it 6 inches into the ground and you have your results in a minute. Nuke gauges are usually the best method for testing this unless traces of mica are heavy into soil, in which it will throw off the nuke gauge reading of the moisture content, in which you would just have to cook it. Nuke gauges have to be used for GAB because it is impossible to drive rings into GAB. For the criteria of this project, each different area has its own specification. Example, the building pad area, where majority of the people are going to be at, where they're sitting there enjoying the show, has to be compacted to 90. Each lift has to be compacted to 98%. The pavement areas, the top 18 inches have to have a compaction percentage of 98 as well. Anything else below those 18 inches can have a compaction percentage of 95. Utility trenches are the same way. Landscape, you have a little bit more leeway with the compaction percentage of 92. The moisture content in the soil has to be plus or minus 3%. Once we backfill the site up to grade, we proof roll the site. We proof rolled the building pad, the parking area to see if there was any pumping or rutting throughout the site. And if there were, then we corrected it and proof rolled it again and made sure that everything was stable, that no pumping, no rutting went on throughout the entirety of the site before we continued with construction. Once construction started and concrete placement was needed, we also inspected the concrete that was being poured on site. We got the temperature of the concrete, we did the slump, we performed the air, we made samples, we got the unit weight, and then we test those samples for compression strength to determine if the concrete was suitable.